In this third part of Lecture 3, we're going to relate internal energy and heat capacity and enthalpy and heat capacity. To set this up, let's first get here. Let's remember that, there we go. From the previous two parts of this Lecture 3, written in the differential form, we said that du is the differential or the infinitesimal heat transferred in a constant volume process, or dH is equal to dq in a constant pressure. If we write this in integrated form, delta H would just be the total heat transferred, delta U, total heat transferred in a constant volume process, and delta H will be equal to the total heat transferred in a constant pressure apparatus. Let me use the eraser, so make this more clear here. This is delta U. All right, now what does delta H, delta U, or du, dH have to do with heat capacity? Well, remember in the second lecture, we said that you can calculate heat transferred as a heat capacity times a delta T. Getting late here, making mistakes. Heat capacity times delta T. So heat, there's heat there. Heat capacity, so these are probably related to heat capacity. In fact, what we're going to show is that delta U is just the integral of the heat capacity dt. And same way with delta H, the integral of the heat capacity. But now we're going to define two kinds of heat capacity, one at constant volume and one at constant pressure. All right, so that's where we're going. So let's start first with this assertion. I'm saying that internal energy is a function of two variables, and those two variables are temperature and volume. This is for PV work. T is related to Q and V is related to PV work. And we'll, when we define two other thermodynamic quantities, Helmholtz free energy and Gibbs free energy, we'll discuss in more detail about these two variables. But right now, U, just think of it as a function both of temperature. If the temperature changes, U changes. Also volume. If volume changes, U changes. All right, so given that, we can now look at the total differential of U. This is how U changes with the first variable, T, at constant second variable, V, times how much temperature changes, plus how U changes with that second variable, V, at constant first variable, T, times dV. Okay, so this is, I don't know if you remember this from calculus or not, but if you have questions, bring it up in class. All right, now we're going to make the assumption that we have constant volume. So constant volume implies that dV is equal to 0. So at constant volume, this term will go to 0. So now we just have du is equal to how U changes with temperature at constant volume times dt. And remember that at a constant volume, this is also equal to QV. So it looks like if we define this as heat capacity times dt, all right, so let's bring these two things out here. If how U changes with temperature at constant volume, if we identify that with a heat capacity, and we'll put a V there to indicate constant volume, then it looks like the heat capacity times dt will give you QV, just like we defined in introductory chemistry and in lecture 2. All right, so if that's the case, then du is, this should be a D. We're looking at differential form here. du is dQV, and that's how internal energy changes with temperature at constant volume times dt. Let's do the integrated form. I'll just rewrite that equation here. du is how U changes with temperature at constant volume times dt. And again, we derive this equation by assuming that we have constant volume, so the dV term went away. Well, let's call that heat capacity CV times dt. So our heat capacity at constant volume is defined as how the internal energy depends on temperature at constant volume. Let's integrate this. So we have the integral of du is just the integral of CV dt. This will, since u is a state function, this will be just delta u. This will be the integral of CV dt. And let's make the assumption that we have a constant heat capacity, so CV times this will be the integral of dt. Our assumption here is constant CV. CV does not depend on temperature, so you can pull it out of the integral. And the integral of dt is just delta t, so this will just be CV delta t. So if we know the heat capacity at constant volume, and we have a temperature change, and the whole process occurs at constant volume, we can calculate the change in internal energy. All right. Let's do the same thing for enthalpy. So I'm going to make the assertion that enthalpy is a function of two variables. It's temperature and not volume, but pressure. If that's the case, the total differential of H is how H changes with temperature at constant second variable pressure times dt, plus how H changes with second variable P at constant first variable temperature times dP. Now we're going to make the assumption constant pressure process. Constant pressure implies that dP goes to 0, so this term will go to 0. So this is equal to just how H changes with temperature at constant pressure times dt. And analogous to what we did for internal energy, we're going to define heat capacity at constant pressure to be equal to how the enthalpy changes with temperature at constant pressure. So this then is equal to just heat capacity at constant pressure times dt. And if we integrate this, just like we did before, the integral of dH, integrate both sides, integral of Cp dt at constant constant Cp. In other words, if Cp does not depend on temperature, you can pull it out of the integral. This implies, as we did for internal energy, delta H is equal to Cp times delta T. Okay, so that's interesting, or maybe not. So we just got that one and got that one. Now, let's go on here. What if Cv is not a constant? Well, if Cv is not a constant, well, what does that mean? Well, we'll say that, we'll start here. Delta U is the integral of Cv dt. And if Cv is not a constant, if it does depend on temperature, you can't pull it out of the integral. It has to stay in the integral. Same way with delta H. Delta H, remember, was the integral of Cp times dt. And if Cp is not a constant, if it does depend on temperature, you can't pull this out. So you have to know how Cv and Cp depend on temperature in order to determine this. If you look up on the internet, you'll find, and let me see if I can put up a page after this lecture, but if you look up the internet, in the chemistry National Institutes of Standards, you'll find, in fact, experimentally determined heat capacities as a function of temperature. You can just plug those in and integrate them. Let me see if I can find that web page. Just a second here.